It is Wednesday, July 12th, 2023, and welcome to this special episode of Fault Lines, where we're kicking off our Summer of AI series here at NSI entitled Breaking Barriers, Understanding the AI Revolution. I'm Jamil Jaffer, NSI's founder and executive director, and today I'm speaking with Dr. Stephen Wolfram. Dr. Wolfram created Mathematica, Wolfram Alpha, and the Wolfram Language. He's the author of A New Kind of Science, the originator of the Wolfram Physics Project, and the founder and CEO of Wolfram Research. He's a spectacular expert here to help us launch the summer series and explain to us the complexities of artificial intelligence.
So, Professor Wolfram, we're thrilled to have you here on NSI's Fault Lines podcast for the beginning of our colloquially called Summer of AI series. And we're just thrilled to have you because you've had a long and storied career in technology, in mathematics. You developed the software program Mathematica, which has been widely utilized. But you've spent a lot of time for the course of your career, and in particular in recent weeks and months, talking about artificial intelligence, machine learning, and explaining to the American people, to the global audience, actually, how AI works, what it does. And so we thought you'd be a perfect first guest to take our audience through what we're seeing in this explosion that we've seen just in the last few months of artificial intelligence and AI in the public domain. So if we could just start at basics, right? What is artificial intelligence? How does it relate to machine learning and all these other models? What is going on here? What is this area of study that we're talking about?
Well, it has a long history. It originated in the 1950s. People, when there were first computers, people thought there will soon be giant electronic brains that will be able to think better than people, just as, machinery can lift logs better than people and so on. This didn't work out. It took a lot longer to get to the point where computers can do kind of human-like things. What developed during that period of time was the whole idea of computation, the whole idea of computers being able to follow rules and compute things, often things that humans cannot do very well.
Right.
And so that developed. Then this idea of neural nets, which is sort of an idealized imitation of how neurons work in our brains. That idea comes from 1943. And again, this slowly developed. And, people like me, I first worked on neural nets back around 1980. Couldn't get them to do anything interesting. Didn't think they would do anything interesting. Then finally in 2012, there was sort of a surprising breakthrough of being able to get neural nets to do things like recognize a picture of a cat from a picture of a dog, which had been something that had been kind of very hard for computers to do. Then the next big breakthrough was just this last year when LLMs, large language models, and ChatGPT and so on suddenly have been able to sort of fluently compose sort of human-like text. And, it's kind of, nobody really saw this coming, including the people working on it. It was a big surprise to everybody that ChatGPT was as sort of linguistically fluent as it is. So, what is it doing? How does it work? Essentially, what it's doing is it says, let me take the web, 4 billion web pages roughly, plus a bunch of scanned books and so on, and let me try and write text that kind of follows along the way that the sort of average text that humans have put on the web follows along. So you might have a sentence like, the cat sat on the, and then the question for the AI is what word comes next? Looking on the web, you find, mat is the most common word. So it's going to say, okay, mat's the most common word. There's a second most common word. Sometimes it'll be set up to pick, not necessarily the most common word. But so essentially what it's trying to do is to write text that's kind of like what would be typical of text that humans have written and put on the web and so on. And the thing that is not obvious, it's a scientifically non-trivial fact, is that you can't deduce next words purely from the statistics of what's on the web, because there just isn't enough stuff on the web to know how sort of every essay continues, so to speak. And so you have to have some kind of model for how that works. This neural net model, which is sort of loosely based on how brains works, seems to be really good and seems to produce sort of essay-like things that are similar to the way that humans would write such essays. And that's it's a non-trivial scientific discovery in a sense that we can use this particular neural net model and get something which kind of behaves in a human-like way.
Well, so let's talk about that. So you mentioned earlier that you first worked on neural nets back in the 1980s. They didn't work particularly well. That there was a big breakthrough in 2012, and then another big breakthrough more recently, just in the last year. What has fundamentally changed, either in technology or in academic or industry understanding of these models, these capabilities, these techniques that has allowed for the development of this more human-like capability? And I want to talk about what human-like means, but let's talk about what's changed fundamentally in technology or understanding that's led to this newer capability.
You know, it's funny because the kind of architecture, people had tried to make sort of elaborate things where they had extra sort of machinery in these neural nets and so on. Most of that didn't turn out to be relevant. There are detailed engineering pieces of cleverness that got added along the way, but the fundamental ideas are very similar to the ideas from the 1940s and are very similar to this idealization of kind of what we observe sort of neurophysiologically in human brains. And the thing that, there are a couple of things. First of all, you can just, you've got faster computers. You can actually do particularly the training. So one of the key features of kind of machine learning is the following, that when you write a program, and you write this program, you set it up to specify how the computer should do things, and sort of you're figuring out what the computer should do. Sort of the idea of machine learning is you just give the computer a whole bunch of examples of what it should do and let it figure out, let it sort of extrapolate from those examples what it should do in a particular case. So it's kind of that's sort of the key idea. And one of the things that's difficult is, can you actually get this computer, this neural net setup, for example, can you get it to learn stuff? You feed it a bunch of web pages. Does it actually learn to write text? Or does it just say, well, that's very nice, but I can't do anything with it? The thing that happened in 2012, it was kind of an accident, actually. People just sort of bashed it harder. They left it running for, they left the computer running for a month, just trying to bash it to say, learn this, learn this, learn this. And eventually it did. Nobody could say when that would happen. It was in fact, one of the things that was a confusing thing is that people for a long time in the 1960s, 1970s, they always tried to simplify the problem of AI. They always tried to say, let's make the computer just try and understand, a world of blocks or something, and that's it. That's its whole world. Turned out that the harder problem was actually easier to solve. That the problem when you fed it sort of real images of cats and dogs and 5,000 other kinds of things, that problem was actually easier to train for than this very sort of idealized problem. So, the specific turned out to be, it was very unusual in science. Usually in science, we try to sort of break off this sort of sub piece that we can study and get that nailed down. What happened in this case was the big problem was actually easier to solve for a technical reason that, again, none of us understood in advance, so to speak, which is you're kind of trying to, when you're doing learning, you're trying to think about it sort of as a mountainscape, and you're trying to find the lowest point on the mountainscape. And you do that by kind of always trying to walk down the mountain. Well, the problem is that many times you get stuck in a mountain lake. You're always trying to walk down the mountain, but you've got to the local minimum, the mountain lake.
Right.
Well, in a regular sort of 2D sort of mountainscape, you can often get stuck. Turns out in these models, you might have a million-dimensional space. And it turns out it's much less likely that you get stuck in a million-dimensional space. So once you have that million-dimensional space, what's that?
So make sure I understand. The larger the problem, you're saying it might actually be simpler to solve. Is there less places to get stuck?
Yes, that's what turned out. So that's what was discovered. So that was a surprise. I mean, that was something where, as I say, the usual push towards sort of scientific reductionism didn't work out in this case. So then, the question of why did we get sort of large language models with intelligible kind of text now, it was a surprise. I mean, even last year, the typical large language model was producing text that was boring, off topic, kind of wandered around. It didn't seem human at all. And then suddenly, as a result of partly again, when one trains the thing, one thing is to say, here are a bunch of web pages, go imitate these web pages. There's another step, usually called reinforcement learning, human feedback, which is a step where you actually get humans to kind of rate the things it's saying. And that can go horribly wrong, and it did go a little bit wrong, because it's just like, let's just pick 30 contractors from California and have them mark off, don't let it say anything shocking. And of course, that doesn't work out perfectly. But nobody thought this would be as big a deal as it turned out to be, so nobody was terribly concerned about that. But that last step of kind of directing it a bit by giving it kind of tutoring, so to speak, rather than just book learning, that turned out to be apparently pretty important in getting something which reaches this point of sort of human intelligibility. I mean, it's kind of like what happened, I guess, in the 1800s with telephony, where everybody had known there would in principle be possible to transmit speech over electrical wires, but then Alexander Graham Bell suddenly managed to get it to be intelligible speech. And it's sort of the same thing that's happened with LLMs here.
Yeah, and so what you're talking about, this idea of sort of humans providing feedback to the machine, that's what I understand is called labeling of data. Is that right?
No, that's a different thing. Labeling is for sort of more general machine learning. So the thing is, when you say, I'm going to get it to recognize cats versus dogs, you have to say, this is a picture of a cat, this is a picture of a dog. It has no way to know just from the pictures what's going on. The trick that is used in text is the following thing, that the kind of task that the machine learns is, you've got a piece of text, just mask off the later parts of the text and have the machine try and figure out, can it predict what things you masked off? And that's kind of a way of doing things where you don't have to do this kind of explicit labeling.
Interesting. And when it gets it right, the human's giving feedback that was a valid answer.
No,
and that's what you're talking about with the reinforcement piece, or no?
No, that's all done automatically. I mean, that's what takes, well, it's unclear how much money it is now, but it used to be tens of millions of dollars of computer time to grind through and say, here's 4 billion web pages, try and make sure you are correctly reproducing the later words in these sentences. That's a part that's done. That's the main part of the training. Then there's an additional piece, which is, okay, now you're ready. You're ready to start writing essays. Humans say, what do you think of these essays? Oh no, this essay went way off track. Oh no, this essay is yakking about things that we don't want the thing to yak about, or whatever. That's a very subtle and difficult area, which is, this question of kind of, what do you want the AIs to do? And it's something which I would say that I consider the things that have been done on that so far extremely primitive. I mean, I think it's a very difficult problem to know kind of how you direct the AIs. It's kind of like, when humans write laws for humans, so to speak, they're sort of trying to direct what humans do. And we have a whole, history in our civilization of how that might work. And I think for the AIs, kind of this question of sort of what should the basic constitution for the AIs be? And there won't be one worldwide such thing. Something which, if you ask many techies, they'll say, no, there's going to be a world constitution for AIs, which I think is a quite unrealistic idea. But, I think that the question of sort of even how you think about creating such a thing, what should it say? These are pretty important questions for the future. I think there are a number of kind of intuitional issues, which, I've worked a lot on basic science, and there's sort of the question of, okay, you set up some rules for an AI or a computational system in general. What happens with those rules? People might say, oh, if I know the rules, if I can see the code, I'll know what the system is going to do. That's not true. That's kind of there's this phenomenon I call computational irreducibility, which is all about the fact that just because you set up particular rules for something doesn't mean you can foresee what the thing will do. It's kind of a conceit of kind of industrial revolution style technology that we can kind of see the gears and see where they go. That's something that we cannot expect to continue.
Yeah, can we talk about that? Because that's been a lot of what I think people have been concerned about is that, sometimes you'll ask in ChatGPT or another AI capability a question, you'll get different responses. And people are wondering, well, how does it come up with these responses? And why, if we've written the rules, if humans have written the rules essentially, or created the neural network, why can't we figure out what gears are turning and why does the result come out differently? I know there may be two different responses to that, but can you help us out a little bit with that?
Yeah, right. I mean, so the question of why it gives a different answer at different times, it turns out that to make non-essays that aren't boringly flat, it's typical that one has a little probabilistic element. One has a little bit of randomness. It's like it ranks the words that it should say next.
Right.
And if you always pick the word it thinks is the best word to say next, you end up with very flat kinds of essays. There's a certain, they're usually called temperature. You inject a certain temperature, a certain randomness into which word gets picked next. And that makes for a more lively essay. So that means you ask for the essay 2 different times, you'll get 2 different essays. You can set it so that it operates at 0 temperature, and there are some reasons, some cases where that's worthwhile. There are then all sorts of crazy details about the way GPUs work that mean it doesn't always give exactly the same result, even when you told it, to do it deterministically. But those are minor issues. The fact is, the code of the AI, so to speak, could be set up to always give you the same thing for the same input. It just turns out that isn't the thing that gives sort of the most lively results, so to speak. But I think,
just looking on that point, one of the things that I know that you've mentioned before is that as you're setting this temperature, the right number for the temperature isn't sort of derived by some theory. It's just what works in practice. Is that right? Is there not really a theory behind why some temperatures get you a better essay than others? It's just what our experience has been in using these large language models.
Yeah. I mean, there is one day there will be kind of an LLM science. It hasn't really gotten started yet. In other words, we don't know why. There are a lot of things that happen with LLMs that are really surprising, that tell us things about the way, sort of the structure of human knowledge, tell us things probably about how brains work. I mean, the fact that LLMs produce things that seem reasonable to us, the alien us, so to speak, the non-human intelligence, so to speak, it might not produce things that seem reasonable to that. It's just matching the way that human intelligence does things. And, we don't have, there's a lot of science that should be done in understanding this. And it's kind of it's really just a very, just now emerging kind of approach where there'll be things where there are sort of idealized models of LLMs. And one of the things that's really surprising is that you can just give an LLM sort of a little bit of a prompt, say, talk like a pirate or something, and it'll go ahead and do that. Nobody really quite knows why just giving it that little bit of prompting is enough to have it kind of change its whole mind about what to do. So, those are some kinds of things. Now, another thing about what's happened with LLMs is, people are sort of surprised that LLMs can follow logic. The fact is that shouldn't be that surprising because, the way Aristotle originally invented logic, presumably, was by looking at a bunch of examples of rhetoric, of text, and just seeing this kind of repeated pattern of how things work in rhetoric that makes sense. Well, the LLM has found the same repeated patterns that Aristotle found. If you ask it to do sort of more mathematical level logic, it won't be able to do that. I mean, one of the things about LLMs is that it's kind of they're sort of very broad in terms of their access to kind of linguistic material, but shallow in terms of their computational ability. So it's kind of like if you say, do this sophisticated computation, the LLM won't be able to do that. What it does is to reproduce kind of this linguistic layer. I mean, I think the way to think about sort of the use of LLMs right now is kind of a linguistic user interface. We've got graphical user interfaces. We've now got a linguistic user interface. You've got 5 points you want to make, but you're going to give a report to somebody about what you're saying, and that the LLM can puff out those 5 points into a big report. Maybe the person who gets the report has 2 things they want to know from that report. They'll use an LLM to kind of crush it down to those 2 things again. But I think,
Got it.
I mean, in terms of sort of what AIs and LLMs mean for the world, I mean, more and more things that get done in the world, it will make sense to get AIs to do them. How will that feel to us, so to speak? Because we're not going to understand what the AIs are doing. And that's not a statement of our sort of, oh, we're too lazy to do it. It's a fundamental statement of this phenomenon of computational irreducibility. You kind of have a choice. You can either let the computation really do what the computation can do, or you can say, no, let me put it in a box, let me constrain it, in which case you don't get the advantage of what the computation can do. So I think there'll be lots of reasons.
Well, I want to talk about that a little bit. So one of the things that go ahead, please finish.
No, go for it.
One of the things that I think makes people somewhat uncomfortable or maybe freaks people out a little bit about artificial intelligence. One is obviously the very human-like nature of it. You mentioned the word human-like a lot. Are these systems thinking in the way that we think about humans thinking? Are they developing intelligence and capabilities? I think people worry about that. One, and then second, you've mentioned that we don't really understand how they work. You've talked about computational irreducibility. If we don't really understand how they work, does that raise some concerns about them doing things that we might worry about? I think this is what has people and members of Congress and people in the White House kind of spun up. Tell us about those pieces of this challenge.
Well, so I mean, in terms of do they do things we don't understand? They are sort of going through computational processes, just like things in nature go through computational processes. We don't understand nature. We have science that tries to tell us certain things about what will happen in nature. It's the same kind of thing here. We've set off something which is kind of like the rules of like natural laws. We're making these things run. Now, for much of human history, we were completely happy to ride horses as ways to get around, even though we didn't understand how horses work inside. And then there's this period of sort of the Industrial Revolution type period where we really could see every gear and see how things operated. And I think the issue is, if you want to see how everything operates and you want to be able to check off, no, it will only do the things we expect it to do, well, then it's not going to be able to do as much as you could let it do, so to speak.
Interesting.
I think you had a first part to that. I've already forgotten what the first part was.
Yeah, the first part was, you talk about the human-like nature of these responses that we're seeing. Yeah.
Yeah, right. So I mean, this question of, okay, you've got this computational system and it's doing things that are human-like. Well, if you open up our brains, you'll see a bunch of, 100 billion neurons firing and doing all sorts of things. You ask the question, that's also a very sort of definite, scientifically explorable in principle kind of thing. I don't think there's that much difference between these things. And if we ask the question, kind of, is there a, is it? I mean, there are many details. There's some very sort of almost technological things that biology has done much better than we currently know how to do with electronics. But I don't think that there's sort of a foundational difference between sort of the kinds of computations that go on in brains and the kinds of computations that go on in AIs. There are detailed differences. I don't think it's something where we should say there are fundamental differences. And when we start saying, but it's just an electronic thing with a bunch of electrical signals going around, well, unfortunately, or fortunately, or whatever, that's what our brains are like too. I mean, that's not the distinction to make. I think the thing to really understand is sort of humans are deciding what's happening right now. We are, we're in charge, so to speak. And when we ask, what I mean, we're with the natural world, for example, we are, we're not in charge of the natural world, so to speak. We are at this point in charge of kind of the AI world, and it's an important issue, sort of what we choose to have the AI world be like. And when it comes to things like sort of the AI constitution issue, it's kind of, one of the things that happens is, how do you determine what the AIs should do? Well, some people say, make them do what the humans do. And then other people say, no, that's a really bad idea. We really want them to be like the humans aspire to be. As soon as you're saying the AIs should be like the humans aspire to be, you're in this incredibly slippery slope of so what should that be like? I think one of the things that we do see, which is a sort of important technological issue right now, is the question of to what extent AI is a collective thing and to what extent it's an individual thing. I mean, one of the things that's happened with search and social media, things like this, is these, for partly accidents of history, partly economic reasons, have become very centralized. And that's, when it comes to sort of, if you're a government and you're setting things up and you kind of have a very collective view of things, having centralized AI is a good thing. If you're, it's kind of like, does everybody get to have their own AI, or is it the big kind of centralized AI that's running things? And that's kind of that's a current sort of technological, almost week by week sort of what's going to happen in terms of how individualized, will we all be able to run a ChatGPT like thing on our individual computers or not? Right. I think the answer will be yes. I think that's fairly important. I think there are sort of economic and other forces that might make people say, and there's a certain amount of rhetoric around, it's really hard to do this stuff, it all has to be centralized and so on. I think that's a fairly important thing in terms of kind of sort of how this plays in different kinds of governmental systems and so on.
Well, Dr. Wolfram, this has been a great introduction to the topic of artificial intelligence and large language models. Really appreciate you taking the time with us.
That's a wrap on part one of our conversation. Thank you so much to Dr. Stephen Wolfram for coming on the podcast and celebrating the first episode of our Summer of AI series with us. Make sure you don't miss part two of my conversation in a special episode to be aired this week on Friday, July 14, 2023, where we'll be talking about AI policy. Thanks to Brooke Aga Khan, Angela Mangione from NSI, and Claude Jennings for the help producing today's episode. This is Fault Lines, the podcast that gets you smart fast on the policy debates shaking up America. We're also up on YouTube, so don't forget to check our smiling faces out there. And if you like what you heard or what you saw, be sure to rate, review, and subscribe, and share with your friends so we can get more people into the Fault Lines crew.